This video is about the enormous pile of reactions wherein the nucleophile and the electrophile are both contained in the same reagent at the same time and attack the same side of the double bond at the same time. So in other words, what we're going to do here is add both the nucleophile and the electrophile at the same time and from the same side of the double bond. And since all of that's happening at the same time and from the same side, we call them Syn Additions. I've already shown you a couple of examples, namely in the hydroboration case, what we're doing is delivering a hydrogen and the boron at the same side at the same time. And later, in a separate step, you do a little bit of magic and you convert the boron to an oxygen in an oxidation state. The delivery of the borane is the key part that ties into this video. The second step just converts the boron to something more useful, the alcohol. Likewise, when I was dealing with the alkynes, the initial introduction of alkynes, I mentioned that there were ways of reducing a triple bond down to a single bond using hydrogen gas and palladium on carbon, but this will also work for double bonds as well. And again, what you're doing is delivering hydrogen simultaneously. Mechanistically, what's going on in this first step is, of course, the double bond serves as a nucleophile and attacks the empty orbital that's on the boron. But when you do that, that makes the boron delta minus, and then that causes this hydrogen to want to be delivered. And so you take the boron hydrogen bond and you take those electrons in that bond, you deliver them to the forming carbocation. So this attack of the double bond on the boron is filling this orbital here, but it's leaving a plus charge to be developing there. And so now the developing minus charge here reacts. And again, both arrows happen at the same time and from the same side. So if this boron was coming in from the top, you would not get this outcome. This is instead the boron having come from the bottom because the methyl is up and the OH ends up down. Anyway, the borane does its attack. The boron sits there. You then throw in some hydrogen peroxide, sodium hydroxide, and water, and eventually that gets converted in a second bit of magic into this material as drawn. Over here, what we have is the same general idea where palladium on carbon and hydrogen gas get together in order to create this reagent. And what you have now is two different hydrogens bound to this palladium surface, and the palladium surface is both a source of electrons and can accept electrons. And so the double bond here ends up attacking this hydrogen. This hydrogen is electrophilic because the electrons in the palladium hydrogen bond can go to become part of the palladium surface, and then simultaneously what that's doing is creating a little bit of an H minus, which can then be delivered to the developing plus all at the same time. And again, this reagent, the complex between hydrogen gas and palladium, is the reagent that's both nucleophilic, delivering an H minus, and electrophilic, accepting electrons from the H at the same time. And this, as drawn, is coming from the top, so that would push the methyl down. And in the case where we're delivering hydrogen, you can't tell what the stereochemistry is at this position, so this would end up being an achiral molecule overall. Obviously, up here, we did create a single enantiomer, but obviously you create both enantiomers at the same time, so you would write that as racemic or plus the other enantiomer. If instead of hydrogen gas what we're doing is delivering deuterium, the other isotope of hydrogen, then the exact same mechanism takes place. This double bond would come and attack this electrophilic deuterium and cause the palladium deuterium bond to be electrons that are bound to palladium, which creates a little bit of a D minus, which then attacks to the developing delta plus. And again, if you had this double bond and the deuterium came from the bottom, you'd end up with this, and you would also potentially attack from the other side and create the other enantiomer. So the moral of the story is, again, that the reagent is both nucleophilic and electrophilic simultaneously, creating a mess of arrows in all of these mechanisms that all lead to the outcome of delivering two things from the same side of the double bond at the same time. Again, this is all stuff you've seen before, and now I'm going to extend it to the new reactions. The reagents in this portion of the video are quite a bit weirder than the ones I've already shown you, but they have within them the same sorts of features. This right here is called a carbene, and it's specifically a lone pair contained in an sp2 orbital. So this is going to be the nucleophilic lone pair, but this is a carbon that contains an empty p orbital at the same time. This specific variety of carbene is called a singlet carbene, and I'll have a video dedicated to showing you exactly how to make this, and there's a couple of different varieties of R groups that we can use. But what happens here is essentially that the double bond will come and attack the empty orbital at the same time as the pair of electrons goes back and attacks, and that leads to a product whereby you have a little triangle installed and a couple of R groups in place. Assuming that the carbene attacked from the top, then the methyl will end up down. The new little cyclopropane triangle that we will install will be right there, and then whatever's bound to the carbon ends up up as the R groups there. And again, there's a couple of different varieties of R groups that you can install depending on how you make the carbene. So there's going to be a couple of different things that you can make, but they all have this general form. And again, the key feature is that you have both an empty orbital while at the same time having a pair of electrons. And so in many ways, this simply resembles the borane that we use in the hydroboration of anti-Markovnikov delivery of water. And again, what you have is an empty orbital simultaneous with containing a pair of electrons. Now in the borane case, it was a boron-hydrogen bond, and in the carbene case, what it is just simply a pair of electrons bound to the carbon, so a lone pair. But again, the key feature is that as the double bond is going to fill this empty orbital, what that's going to do is create an area of minus charge on the carbon. That area of minus charge will then come in and deliver to the area of plus charge that's growing in as you use the double bond here. One thing I want to point out about the carbenes is that they are explicitly and formally neutral species because they contain 4 electrons that belong to the carbon, but they are extremely reactive because they only have 6 electrons total around this carbon. 2 in this R group bond, 2 in this carbon R group bond, and then a pair of electrons. So again, only 6 electrons total, much like borane, but an empty orbital and a pair of electrons. So it can be attacked, the empty orbital, the electrophile, while delivering the lone pair, the nucleophile, simultaneously. And again, the key feature for all of this chemistry is that the same reagent has both a nucleophilic and an electrophilic end simultaneously. What we have here is going to be something that forms a weird little triangle, but in this case, the little triangle contains an oxygen, and we call this an epoxide. And again, assuming that we're dealing with the one that came from the top, then the oxygen is explicitly going to be up. And I will have a video dedicated to the reactions of epoxides. This will turn out to be really helpful for synthesis later. You can use all kinds of organometallic reagents to open epoxides in a way that's useful for stitching carbon-carbon bonds together. Or, for example, with the chemistry you already know, an alkyne with a minus charge on it, an alkyne can come and open the epoxide from the less hindered end. And so you can use epoxides in synthesis. Now, what's going on here mechanistically, it's not obvious where the electrophile is unless you've watched the magic video that deals with the oxidation of a borane. And in there, I told you that a oxygen-oxygen bond is an exceptionally weak bond. So what that really wants to do is that wants to fragment to give that oxygen a lone pair. So what's going to happen there is that's going to be the bond that breaks. So that means that this oxygen is actually electrophilic, which is kind of a weird thought. Now in practice, you don't have the oxygen-oxygen bond become a lone pair. Instead, what happens is this ends up becoming the double bond while this abstracts this hydrogen, all of which creates a bit of a minus charge on this oxygen that can be delivered all at the same time to create the new forming epoxide. The reagent that I'm using here is metachloroperoxybenzoic acid, mCPBA. Peroxides are extremely dangerous. They're highly reactive. They definitely want to go boom. They're fairly toxic. They will do damage to your skin and stuff like that. So anyway, peroxides are no fun at all, but mCPBA has the advantage of being a nice solid that you can purchase and that's relatively stable, and they can deliver a bottle of it to you and so on when you buy it from Aldrich. So in any event, this is a reagent you definitely need to know. mCPBA is the standard way of making epoxides, and basically you've got all 4 of these arrows happening simultaneously, but what I really want you to know is that you can take a double bond and turn it into an epoxide, an oxirane, this kind of little triangle with an oxygen in the corner. Any peroxide will do the same thing. TriFluoroPerOxyAcetic acid would be another example, and again, this double bond could come and break the oxygen-oxygen bond by attacking that oxygen. That would then lead to the formation of a double bond there, which would cause this to come and abstract this hydrogen, which causes this to deliver. And of course, you'd end up making the other enantiomer of this material. In both cases, whether you're doing carbene or delivering an epoxide, of course, it's going to be non-selective. You're going to be making racemic products. You're going to be making both enantiomers along the way. But again, the key feature in both cases is that the reagent is electrophilic and nucleophilic at the same time. In the case of a carbene, it has the very definition of an electrophile, an empty orbital, as well as the very definition of a nucleophile, a lone pair, at the same time, and it's obvious, and those get delivered at the same time, and you only need 2 arrows. In the case of mCPBA and TriFluoroPerOxyAcetic acid, what's going on there is that you have sort of a hidden electrophile, an exceptionally weak bond that can be fragmented if attacked, and also a hidden nucleophile. This OH bond can become the thing that attacks if you abstract that hydrogen simultaneously. Notice how organized these transition states are. This needs to be oriented just the right way when it bounces into the double bond in order to deliver it. On the other hand, all this set of four arrows can happen all at the same time because this is a relatively likely orientation of things. So anyway, this is a reaction that takes place from the same time of the double bond at the same time, and therefore all of this leads to the formation of the little triangle type species, whether oxygen or in the case of the carbene with a carbon. I'm going to finish off this video with a couple of different Syn additions that are a little bit trickier to see while you have the nucleophile and the electrophile together at the same time. But in the case of the osmium, it's much like the palladium, where whenever you have a metal, it has the capacity to both donate and accept electrons pretty easily, and we're going to take advantage of that. And then in the case of ozone, we're fundamentally taking advantage of the property of oxygen-oxygen bonds of being exceptionally weak, much like we just did with the peroxide and so on. So anyhow, these are just extensions of that same idea that the same reagent has both a nucleophilic and an electrophilic end. With the case of osmium tetraoxide, what you're doing is delivering two oxygens simultaneously across the double bond, and again, they're going to be on the same side at the same time. And osmium tetraoxide is just horrifically expensive, incredibly expensive stuff, so we never use it stoichiometrically. Instead, you use water and hydroxide and then some other stoichiometric oxidant, so that you basically get to use a tiny amount of the osmium and you use up all this other stuff to create what's going to make this go. And again, the mechanism isn't really the point, but what's going on here is that the double bond is attacking one of these oxygens, which causes the double bond there to deliver its electrons to the osmium, but at the same time that then causes another electron to go ahead and add, and the end result is that you end up making an intermediate that basically just looks like this. And the only part of the magic involved here is really that first step, because everything that happens from this point on could be understood by chemistry you already know, with like a hydroxide attacking the osmium and then shuffling protons around and so on and so forth. And so there's really nothing magical about this step at all. It's just, this isn't the point. And so, you know, as far as I'm concerned, what you really need to know here is that osmium tetroxide adds two alcohols at the same time. So all of this stuff is fine, and I'm showing it to you now because it fits into the same general category of Syn additions, where the reagent has both a nucleophilic and electrophilic end simultaneously. But in practice, what I need you to know here is not mechanistic stuff, just this predict the product sort of information. Take double bond, add osmium, what you end up doing is a dihydroxylation, two alcohols from the same side of the double bond simultaneously. O3, definitely weird. Definitely, even after I show you all the details in a separate video, you're going to end up looking at this black box here and saying, you know what, I'm fine with that being a black box. I think it's baloney, it smells fishy, I don't like it, and so on. But what's going on there is fundamentally you're snipping this double bond. I like to think of ozone as being molecular scissors for double bonds. It just goes right there and snip, takes care of it. And again, I'll walk through how you get there just because I think it's fun and interesting, and it again illustrates the main points that I want you to take away from this. But the core idea is that you go through this magical thing, and then there are three different ways of working up this black box intermediate, and that's what this is good for, the predict the product sort of stuff. So again, what you're going to do for ozone every single time is you're going to end up clipping right there, right through that double bond is where you end up clipping. Now, what you really need to do always in an ozone problem is number the carbons, and so I'm going to do this rather arbitrarily, like so. This isn't necessarily good numbering for the purposes of naming this compound, but that's going to help you figure out what I have done over here. So the main workup that you need to know is if you add zinc or dimethyl sulfide, what it ends up doing is converting the double bond carbon into double bond oxygens at both places. So at position 1, we had a hydrogen lurking there, which means that that's going to become an aldehyde. So that's position 1. And so the result of doing a two-step sequence with ozone and zinc or dimethyl sulfide, one or the other, is that wherever you had a sort of mono-substituted end of the double bond, you end up making the aldehyde. If you had a hydrogen there, you still have a hydrogen there, and now it's an aldehyde. And then 2, 3, 4, 5, they're unaffected, but 6 was again part of the double bond, and now it's a ketone. So anyway, it converts CC double bonds into pairs of CO double bonds like that. And again, this is the most useful synthetically for us because in organic chemistry 1, you really don't have mechanisms by which you can make aldehydes and ketones easily, and so you need a tool that allows you to do stuff like that, and this is that tool. But if you instead take this material, subject it to ozone, make the weird intermediates, and make the hydrogen peroxide workup, what that's going to do is oxidize everything up to the highest possible oxidation state. So your ketone is going to remain a ketone because that's at the highest oxidation state you can get. Carbon 6 is as oxidized as it could be. But what it does is convert position 1 into a carboxylic acid. You basically insert another oxygen into that bond right there, and that then leads to your final product, which is again going to be ketone as the max max you can be on the one side, and carboxylic acid as the max you could be on the other side. And again, hydrogen peroxide is oxidizing this material, taking you up in oxidation state. With a mild reducing agent like zinc or dimethyl sulfide, you make aldehydes and ketones. With hydrogen peroxide, a strong oxidizing agent, what you're doing is making acids and ketones. And then, of course, the last option we have here is sodium borohydride. And what that's going to do is convert everything into the alcohol. So this is a reducing agent. This will take you down in oxidation state, and it's going to give you a racemic mixture in this case because you make both enantiomers of the alcohol at position 6, but position 1 gives you a primary alcohol. So anyway, the outcome is this diol that looks like this. So the key feature of ozone is you end up clipping the double bonds, creating, again, this black box intermediate, which then you can mildly reduce to aldehyde and ketone. You can oxidize to acid and ketone, or you can reduce fully with sodium borohydride to the diol. As always, the key feature of any sort of mechanistic work is the Lewis structure, good Lewis structure that you end up drawing for whatever reagents you have over the arrow. So in the case of ozone, even though it's formally neutral, what's the important feature here is that the oxygen in the middle ends up formally plus, and the oxygens on the ends end up formally minus. But the key feature is that you have a lot of oxygen-oxygen bonds, and those are relatively weak bonds. And so what's going to happen here is that this double bond will end up attacking this oxygen on the end, and that will cause this bond to become a lone pair on the oxygen in the middle, which is going to be a good thing as far as this oxygen is concerned. But as you're doing that, you're creating a big delta plus at the tertiary position, so this nearby oxygen that has a minus on it will just go ahead and bond in right there. And so one of the key things that I'm going to draw in this box is not, in fact, where you end up. This isn't the final place where we will go. Some other magic will happen instead, but I did want to at least show what that intermediate step looks like as soon as you form it. So after this sequence of arrows has taken place, what you're left with now is an intermediate that should look incredibly bizarre to you, but it does at least have the advantage of each oxygen having a full octet and formally neutral. So anyway, this is happier than we were before, which is why this takes place. This is not, in fact, the material that goes on to do the rest of this stuff. There's more magic that happens in there. I'll walk through that. But if there's one thing I want you to take away from this video, it's that you can attack a double bond simultaneously from both directions at the same time if one end is nucleophilic and one end is electrophilic. Specifically, the electrophilic end gets attacked by the double bond, but that will create a plus on the double bond, so the nucleophile comes in and adds at the same time. And that's what leads to all of this chemistry. And again, I'm not necessarily as interested in the mechanism for much of this chemistry because a lot of it's very weird stuff, but I want you to recognize that this is kind of how this chemistry all works, and to therefore help you lock that information away for predict the product sort of problem.